Right, one of the most commonly used continuous distributions we use in statistics after the normal curve, which dominates a lot of what we do. But after the normal curve in engineering, the exponential distribution is of particular interest to us. We use it in reliability to look at failure rates and hazards related to our engineering projects. But another common use is to really look at arrival rates. You can think of the arrival rate of a defect as a form of use of exponential. How often does something fail is really an arrival rate. But typically in engineering, we often want to pair the exponential with a Poisson distribution, which was one of our discrete distributions in a prior unit. So let's just take a look at how we would do that. Let's assume first that we have some process. It can be a process where an event happens. It could be people queuing up at a movie theater or an ATM. It could be the arrival of a transaction over a network. Any number of things. But for the sake of argument, let's assume we have a Poisson process where our NP, our expected value, is 20. We're expecting something to happen 20 times per hour. So as with any distribution, what we're concerned with is that a systemic rate? Or is that an average of multiple varying processes that we already understand? So perhaps things arrive a lot more frequently during a rush hour and a lot less frequency off hours. If you have reason to think that this number is an average across an extended period where over at different periods different rates would apply, then you don't have a single Poisson or naturally occurring process. But if the 20 is a naturally occurring rate, you have no reason to think that any other time or any other place it would be any different. We can apply the distribution to our analysis. So if that's the case, we can then do a Poisson analysis to see how many should arrive at any given time, because 20 arriving per hour is in fact an average. In a discrete distribution, our x will go from 0 up to some arbitrary number as high as we want. I think I've taken it up to 60 in this particular spreadsheet. So I start by saying, what would my x be? And if I know that, then I can calculate my Poisson probability. So I'm going to use in these cells, I'm using the Poisson function in Excel, where the first parameter is the x value in column A, the second parameter is the NP, or the expected value, in column B3, and I'm putting false on this one because I'm not interested in the cumulative probability. I'm interested just in the probability of 0 arriving. So if I'm expecting 20 to arrive, what's the probability of 0 arriving? The probability of 10 arriving, down here on row 17, is just over 0.58%. So I really do expect more than 10 to arrive. Down here on the arrival of 20, I have an arrival rate of just over 8%. So it's depicted here in the curve. I can graph that number, and sure enough, the mean of the curve is at the expected value of 20. But I really, looking at the curve, would expect to have some hours where only 9 arrive and some hours where 33 arrive, and obviously the tails go off forever as I go through. So I've plotted the probability of any particular value happening, and very often in our analysis what we're interested in is the probability of that number or less. So the cumulative probability I can then calculate using the same binomial function to pull in the x value and the average parameter. Only in this case the third parameter is true, meaning I want the cumulative probability. So the lower graph here shows the cumulative probability that by the time I get up to 30 or more, chances are I will have exhausted my data. So it corresponds to the tail on the individual probability. So that if I want to know from my expected 20, what's the probability of actually getting 20, it's not quite 9%. But the probability of getting 20 or less is already at roughly 56%. So it's a skewed distribution. The tail over here on the right is much longer than the tail on the left. So my median value is to that right. So my median value is someplace right around the mean, but it's a 56% probability that 20 or fewer will arrive. Now, we use the Poisson distribution for a lot of things in terms of arrival rates. In industrial engineering, we use it very, very heavily because you can't just design a process to handle 20 per hour because you might have hours where you get 10 and you'll actually get that. That's what's going to happen roughly 1% of the time. Or you'll have hours where a lot more than that occur. How about 30? The probability of 30 arriving is almost 1%. So I'm going to get variation in the amount that arrives. I can't just design my process to always process 20 because I'm measuring time here and I can't reclaim that. So if I build my process to handle 20 per hour and only 10 arrive, I have excess capacity for 10 more, but I don't get to use that capacity in the next hour. That capacity is wasted. Likewise, if I design my system to handle 30, most of the time I'm going to have a lot less than 30. So I'm not going to have a queue, but I'm going to have a lot of extra capacity. So we're always in engineering trying to trade off excess capacity against queue length. And what's the probability of having a long queue? Typically, it's a complex phenomena. I'll typically use a discrete simulation to model it. Because if I have an hour where only 10 arrive, I've got some extra capacity and it tends to go to waste. If I have another hour where I have 30 arrive, I'm using all of my capacity at 20 and I have 10 people waiting in line at some point on average. But if in the next hour only 10 arrive, then I not only handle those 10, but I clear the queue. So often we're using a distribution here to try to calculate hour after hour in a discrete simulation of what's the probability I'll have more than 20 for successive hours, because that's where the queue grows. As long as in 1 hour I have more, but in the next hour I have less, the average queue length will stay fairly short and you won't have to wait very long in line. But if I were to have 2 or 3 hours in a row where I have more than 20, my queue would get very significant. Clearly, I'm not handling the capacity at that point. And it could happen, and I can use these probabilities to distribute that. But even there, I'm calculating based on an average. And you're looking at the Poisson of 20 per hour. That's about 3 minutes each. I'm assuming that everything will happen roughly 3 minutes apart. And probabilistically, I should really be checking that as I go. So what is the mean time between one customer arriving or transaction arriving and the next one arriving? To get at that, I move past the Poisson distribution, and I'm going to start to use an exponential distribution. So bringing back in now a continuous function, the exponential distribution I should always do in the same scale that I'm doing in the Poisson calculation. So my scale is going to be an hour, and my lambda, my expected value, is 20 per hour. I'm taking that value directly off of the Poisson calculation. And in the exponential, one of the numbers of interest is obviously the average, or the mu, associated with that process. So if I'm processing 20 per hour, the inverse of that, literally 1 over that value, is 0.05. So I have 0.05 hours per transaction is allowed. In my text, I've translated that into the minutes that are going on, but multiplying that by 60 just so I can have something visual. So I'm expecting these arrivals to happen every 3 minutes, but do they actually happen every 3 minutes? Because while I might have my capacity from the Poisson conversation is to be able to handle 20 per hour, I've got to be careful of saying, well, whatever that process is, whatever it takes to process that transaction can take 3 minutes, because my events are going to happen 3 minutes apart. So is it a good idea to use up those 3 minutes? Well, if the events happen more often than 3 minutes, maybe arrive at 2-minute intervals, then if I take 3 minutes to do the process, I'm going to build up a queue again, even if they're arriving at the 20 per hour or less of the Poisson distribution. So Poisson works on that capacity 20 if on average someone arrives every 3 minutes. But what if I have a string of people that walk in the door? I only get 10 in an hour, but they all walk in less than a minute apart. I suddenly have a queue again because my process takes longer than the gap between them, even though I'm within my capacity. So you can see how the Poisson arrival rate of transactions interacts with the exponential rate of when those transactions arrive, and therefore how long I can take to process one of them. So I would use the exponential distribution to do that. So again, I'm going to have my x column. Now in this case, I want to really have two x columns. The first is to figure out what's the scale that I want to talk about. And if things happen 20 per hour, and I know I'm looking at 3 minutes every 3 minutes, I know that I want to be able to have a conversation that I measure in minutes. So the x that I'm interested in is in minutes, and that's going to be anything from 0 to some number of minutes. I've taken 28 minutes here. So I know I want to be able to talk about minutes, but minutes are not the scale of the parameters that I'm given. So I have to convert and know what my x is in hours, because the scale of the distribution is in hours, and I need to plug hours into the formula as I go. So I've simply got a formula here where I can take the number of minutes divided by 60 to convert that into hours. And that's the number I'm going to need when I do my distribution. So I can do the functional distribution on the exponential, which again shows the height of the curve at that point, but doesn't deal with the probability. I can look at the probability, the cumulative probability to that point, and I'm going to see that the probability climbs toward 1 very, very quickly as I go through. So the expected value is 0.05. If I were to look at that, I'm going to see that at the 0.05, the probability is 0.632. It just so happens that the probability at the expected value is always 0.632. This is a very fixed distribution. The exponential distribution doesn't have a lot of parameters, so you don't see changes in the values as you go through on these kinds of parameters. If the mu value always corresponds to 63.2%. There will be other distributions that you want to be able to stretch and contract and scale in different ways using scale parameters and location parameters. And when you do that, you're stretching and moving the curve, and obviously the mu value won't correspond to that. It only corresponds to 0.632 here on the exponential. So you'll be looking at the Weibull distribution and the gamma distribution to do that kind of work. So if the probabilities you're getting here aren't quite what you're looking for, it doesn't fit your data, just don't use the exponential curve, because those larger scales, the Poisson, the Weibull, so certain other parameters are driven by multiple parameters that you can stretch and scale, location and scale of your curve. There's an alpha and a beta parameter to those distributions that you don't see here. Basically, the exponential is a Weibull where you set those parameters to 1. Likewise with the gamma distribution. So there aren't extra parameters here. This is a very fixed distribution, but it works most of the time. When it doesn't, you'll need to extrapolate out, use one of the other distributions, and find the alpha beta that best fits your data. This one, because it only has that one lambda function, and I already had lambda for my Poisson distribution, it's a very, very simple distribution to use. When I add one more layer here, I'm going to add my cumulative distribution. That's what I get the probability of there being more. So again, the cumulative distribution is simply 1 minus the cumulative distribution at that point. So I can have 6. So at 3 minutes, okay, is a 63.2% chance that my transactions will arrive 3 minutes or less apart. There's a 36% chance, 36.8% chance they will arrive more than 3 minutes apart. So that's basically where my probabilities come from as I go. So again, if we have that situation where perhaps 10 customers arrive over here on the left, so I know the probability is about a 1% chance that I'm going to get 10 or less, in which case my process can take longer. But what if I get only 10 people, meaning well within my capacity, but I have a pretty significant chance, 28% chance, they will actually arrive only 1 minute apart. So the exponential curve is very heavy. It's a right skewed distribution, so you've got a lot of values here to the left. So like I said, 63% of the curve is to the left of the mean. So there's a pretty good chance you're going to get things arriving closer together than that 3 minutes. So for queue management, capacity management, for reliability management, we want to know how many events we're going to be handling. And to really simulate them properly, we have to know something from the exponential curve about how quickly they will arrive, how much they will tend to back up, or how often they'll extend out over an extended period. So these curves give you that, and the only parameter we need to enter is the mu value over here in B2. And if I were to change to a different scale than hours, I'd have to come down here and modify this formula that I use to get my hours. Because it's set up right now just to convert minutes into hours. You have to change that formula if you're trying to do months and years or quarters and months and things like that. There's often a conversion that goes on in terms of that. But the challenge here was to come up with column K first, which is the units you want to be able to talk about. So when I say the probability is 81% of something arriving within 5 minutes or less, I'm looking at this column, even though the 81% was calculated using the hours column, but I'm always going to talk in terms of the minutes column as I go through, and that's perfectly fine because those two columns are equivalent. What you don't want to do is when you calculate the probability here on this line, don't ever give it the 5. The 5 is not in the same scale as the Poisson distribution. So while the Excel function will give you a quantitative value, it will not be the probability you're really looking for. So always make sure the number you plug in as the first parameter of an exponential is a number in the same scale as your original lambda. Otherwise, you're just creating nonsense, but it will look like very clean, well-established nonsense. So be very careful how you enter these numbers as you go through. And again, I often say if you don't want the distribution, the height of the curve for the function of that, simply don't populate those cells as you come through, and you'll have just the probabilities that you want. So either way, you can populate your data and use the Poisson distribution and the exponential distribution together in tandem. They help you govern queue management, capacity management, and a lot of your reliability measures coming through.